Welcome to our third and final lesson of Module 1 in Electrical Protection 3. So, in this lesson, we're going to cover the following points. The first one being, what requirements do we need to make sure that we comply with in order for our protection schemes to be effective? The second point being, how we go about detecting abnormal conditions in our power system, and then is going to be discussing the components that are utilized in our protection systems. And the very last point will be for the students to go into the textbook, which is called Introduction to Power System Protection by J.J. Walker, and do exercise 1 that is in the textbook. And if I am looking correctly on the textbook, that should have about 13 questions for you guys to do. Then a day after this, we will be able to schedule for our lesson, and I will give you a tutorial to do. So our requirements for protection scheme is that they need to be reliable. They need to give us an option of selectivity, which means that we need to be able to say what we want the protection scheme to do and when we want it to be done. It needs to provide us with stability. At the moment, we have a lot of network issues, either be it load shedding or be it faults that are happening, and there is on and off of switching that can happen. So through all of that, you want your protection scheme to be stable so that when it has to actually act, it is able to do so. You want it to clear all your faults as speedily as possible, and you want to have some sensitivity into it so that it does not clear fault outside its boundaries, but it looks at the boundary that you are trying to protect. You need it to be very simple so that it's easy for the operators on the field to be able to correct or to be able to manipulate if there is things that need to be changed. And of course, it needs to be economical because everything comes down to cost at the end of the day. If it's very expensive, then your companies will not be able to buy it, and therefore you will not be able to have what you need. So the next couple of slides, I'm going to be going through these requirements. And the first one having been reliability. And in reliability, we're saying that your system should be designed and it should be managed such that it delivers energy to your utilization points in a reliable manner. You always wanting to receive your energy if you are the consumer or the customer. You want your system to be viable. And for it to be viable, it will be done while the cost is less than the value of it to the consumer. You want to ensure that you have got security of supply, and that can be improved by improving your plant design, increasing your space capacity margin, as well as arranging an alternate supply. So this, in a nutshell, will be able to give you a reliable system for you to utilize. So we also said we wanted selectivity. And when we talk about protection, we usually arrange it in zones. And zones, all that it means is that you're wanting to be if you've got a network that is feeding 100 customers, then you zone your network so that maybe you're looking at bunches of 10 customers each, and the rest has got its own zone. That way, it makes it easier for you to be able to say, look at zone 10, which is feeding the customers that are at BCM Wusu. Okay, whereas zone 1 could be feeding somewhere in Amalinda. So that's why we zone it so that you can know exactly where you are wanting to look at your system and where the fault has actually occurred. Then you also say that for your selectivity under your fault conditions, the protection is required to select and trip only your nearest circuit breakers. So if you have a line where you come from a substation and you're going to a customer X, and that line is 100 kilometers, for example. And within that line, you will have other customers that you are feeding along the way. And if a fault exists somewhere closer to customer X, which means, let's say, somewhere at 80 kilometers of the line, your fault is existing, then you only want the breaker just before the fault to be able to open and trip the circuit so that your customers from your substation up until as close as possible to that 80 kilometers, they would still have supply of electricity and not all be taken off. And this selectivity can simply be done by the way that we did or looked at discrimination. So, what stability means is that you want your system to remain intact. In the case that your load is going to be changing, sometimes it goes up, sometimes it goes down. You want to make sure that your system is still intact, that your customers are still getting their supply. You want it to be intact, irregardless of the zones next to your system are tripping, but you want the zone where you are at or where you are looking at these customers where there is no fault, it needs to remain in place. And when we talk about the speed of protection, it needs to be such that your protection must isolate your fault in a quicker manner than it would take you as a person to go out and isolate that fault. So, in other words, you want to safeguard your network, the rest of your network, by ensuring that you remove the disturbances from your system as soon as possible. And what would happen if you do not remove that fault or disturbance as soon as possible? It simply means that you could end up causing major damage to some of your major equipment. And that's what you need to try and minimize. Because remember, what we had said about protection is that it needs to be able to remove it as speedily as possible so that you ensure you minimize the damage, number one, to the point of where the fault has occurred in order for you to be able to do repairs that are going to be minimal. Secondly, you need to minimize it so that it does not spread and go to the rest of the network, as it will mean that you will have more things that you need to repair and replace, and that could cause you a lot of money to lose. So when we talk about sensitivity, we're basically saying that your relays that you are utilizing, they need to be able to utilize as little current as possible for them to be able to operate, so that your consumption of your volt or your amperes must be minimum, and it will then allow you to be able to utilize that relay even if you've got disturbances happening on your network, even if you have faults that make you switch off that network, but because they're operating at such a minimal value, the relays will be able to stay intact. Then we talk about simplicity. And really, all that this means is that your relaying system should be simple so that we can be able to maintain it. And reliability is closely related to your simplicity, because the simpler the protection scheme, then the greater will be its reliability. If your protection scheme is complicated, it's got too many things that say if this happens, then this must go, if that happens, then that must happen, then it means that you have got a huge chance of errors happening and your relays actually tripping when there is no actual fault or there is no need for them to trip, and therefore they become very complicated. Then this is where the crux of the matter is, because we need to talk about money. And the most important factor in your choice of a particular protection scheme is going to have to be an economic aspect. So sometimes it is economically unjustified to use the ideal scheme that you would want to use as an engineer, and you need to then find a compromise. And as a rule, we say that your protective gear should not cost more than 5% of what your network is costing. So if you have a network where you've got a transformer and you've got feeders and lines, overhead lines going to your rural areas, and if all of that cost is saying, let's say it's 5 million, then we're saying the protection that you choose there can cost you up to 5% of 5 million, and it should not cost you more than that. So when the apparatus to be protected is of utmost importance, such as your generators that you have at generation or your main transmission line, we say that these economic considerations, sometimes we subordinate them to reliability. In other words, we're saying we might go over the 5% threshold because we want at that level to have a better reliability than you would want at a distribution level. Because remember, a generation, if you lose a generator, you are going to lose a lot of customers, and that's why we end up going to load shedding, because all of a sudden the capacity is not meeting the demand side. So that's why we're saying for the greater assets, sometimes we say that cost is negligent and our reliability of your system is going to be the one that takes effect or more important. So in this section, we are looking at ways of exactly how do we go about detecting these abnormal conditions in our power system. In other words, where do we put the devices so that we can ensure we are able to provide this protection that is. So firstly, we have what we call the overcurrent, and really this is protection against excess current. And if you refer back to our slides or back to our lesson 2, and when we talked about discrimination by current magnitude, that's how we do overcurrent. Then we have our earth fault detection, and this is obtained by using a relay that responds only to residual current in the system. And what is residual current in the system? That is an electric current which flows briefly in a circuit after your voltage is reduced to zero. And why would you have voltages reduced to zero in your system? It could be due to a momentum of your charge carriers. Okay, so when there was a charge going in the system, it could have been from lightning, then your voltage would all of a sudden be reduced to zero, and that's where our earth fault detection should be able to come in. Then we talk about the current balance. And for the current balance, if you can see on the picture in front of you, what you have is you've got CTs on the left and the right, and those CTs are then connected to a relay that's right in the middle of them. And then there's a circuit breaker, which is the X in blue, that is connected to this relay. So in this case, we say that the CTs at both ends of that line that is protected, and then the relay connected across your equipotential points, and it will not operate as long as those points remain equal. But if you have a fault that is happening within that line between your two CTs, then what you are going to have is that your balance is going to be disturbed. And the minute that your balance is going to be disturbed, then you are going to have the current that will operate your relay. And once your relay is operating, then it will be sending a signal to the circuit breaker in order for the circuit breaker to trip. Then we have what we call the opposed voltage. And in the opposed voltage, now just look at the diagram compared to the current balance that we just came from. So in this one, you're going to have CTs again, where you are having a line, and now instead you have relays connected to each of the CTs. The previous one, you had one relay connected between the CTs. So now you've got a relay connected on each CT, and from that relay, you've got a circuit breaker connected on each side. So if you don't have a fault in this entire system, then your currents entering and exiting will be equal in phase and magnitude, and so therefore nothing will happen. Everything is in balance. But then your CTs will get utilized to produce secondary voltage that is proportional to your primary current. And if no fault, then your secondary voltage will simply be equal and opposite, and no current flows in your relays. But should you have a fault that occurs, it will disturb your balance between the two ends, and therefore then, in this case, your CT secondary voltage will no longer balance. And because that voltage no longer balance on the secondary side of your CT, the current will flow in the relay and it will trip the circuit breaker. And guess what? Because there's two relays, it will trip both relays, will then send a signal to your both circuit breakers to trip, and this entire line will be out. So if on the other side of your circuit breakers there were other networks, because sometimes you have interconnected networks, then those networks will still be running and be in the system, but only this line will have been taken out of that entire system. Then we have what we call phase comparison. And all that it does, it compares the phases, which is your angles on your circuit's ends. And normally your phase angle between your current at the two ends will have a displacement of 0. So in a balanced situation, you want to have a phase angle of 0 between your two ends. But should you have an internal fault scenario, then that displacement will approach 180 degrees. So you can definitely say that once you've gone over 90 degrees going towards 180, you must know that there is a fault and your system more or less soon should be able to trip. Then the last section of this lesson is when we're looking at the components of your protection system. In other words, what do we utilize in order for us to achieve protection in our power systems? We use things that are called relays, and I've been talking about them. And in the next slides, we're going to briefly explain what each of these components are. We also utilize your CTs, which is your current transformers, your voltage transformers, or VTs. Then you've got circuit breakers and your fuses, amongst other things. Then your relays basically is a protective device that will detect the fault and initiate the operation of your circuit breaker. So that's why I was saying that the relay will then send a signal to the circuit breaker for it to trip. And so therefore, once it sends that to the circuit breaker, it means that your circuit breaker needs to isolate the defective element from the rest of your system. Then the detection is done by constantly measuring your electrical quantities, which are different under your normal and your fault conditions. And the measuring is not done by the relay, but it's done by your CTs and it's done by your VTs. So in the diagram that you see below, you've got a circuit breaker, you've got a bus bar, goes down to a circuit breaker, then there's a CT. And if you can see at the bottom, it says now there was a fault that was introduced into the system. So the CT has been reading continuously and there has been nothing happening. All of a sudden, your system gets a fault, and now your CT needs to pick up that fault, and it sends that there is now an abnormal current that I'm receiving in my system. It sends that information to your relay. So the relay now picks up and says, oh, my normal situation is 100 amps, and now my CT is picking up 160 amps. So therefore, it will then send a trip coil. There's a trip coil above your relay that will now close, and the minute that contact, it's a contact, the contact closes, the signal gets sent to your trip coil, and then that trip coil will energize the contact of your circuit breaker, and that's how your circuit breaker would be able to operate in the system. Your current transformer is simply an instrument that we utilize which is designed to produce an alternating current in its secondary windings. And that alternating current must be proportional to the current that is being measured in your primary. But all it does is that it gives it such to a low value of either 1 or a 5 so that we can easily be able to put in simple and small numbers into our relays. So they reduce your high voltage currents to a much lower value and provide a convenient way of safely monitoring the actual electrical current that is flowing into your transmission line. So then we have your voltage transformers, which are VTs, and back in the day, they were called your potential transformers. That's what the PT is there for. Because when you do your investigation, sometimes you will see them still referred to as PTs. So what they do is similar to what the CTs are doing. They're scaling down your voltage on your primary side to a small value that we can utilize on our on our relays. And usually we utilize 110 volts on our secondary side. And remember, our systems can be anything from 1 kilovolt, 11 kilovolts, 33 kilovolts, 22 kilovolts, 66, 132, and even higher voltages as we go up to transmission networks. And ideally, your VTs get connected to a sensing device that has got infinite impedance, and they really usually utilized more on transient disturbances. So that, remember, transient, we said we're not permanent faults. So that at that moment in time that something is happening and the VT is sensing that I'm now out of balance, it can send a signal to the relay to operate, but then the relay can be able to come back on because you'll have your auto reclosing that gets done onto it. Then we talk about our circuit breakers. And what a circuit breaker is that piece of equipment that can make or break a circuit either manually or remote control under your normal conditions. That's the first one. So under normal conditions, you can either close or open a circuit. Then again, it can break a circuit automatically under fault conditions. And in protection, we really look at the automatic function. And in what I've told you now, we usually connect our circuit breakers to your relays. But if you go to your houses where your distribution board is inside your house, then all of those switches that you see there, sometimes white, sometimes green, those are called circuit breakers, but they're of a smaller scale and they don't require the relay to be connected to it. They have that built into them so that the minute your house or your plugs or your lights, they go in an abnormal way, then it will quickly just trip. So that is under fault condition, it will break your circuit. Also, your circuit breakers can make a circuit either manually or by a remote control under fault conditions. So you can, as an operator, go and click it in order for it to open if there is a fault condition. But for an effective protection system, you must know number 2 is the way to go. Then we have fuses as our last one that we're going to be looking at, and these are widely utilized for interruption of fault currents, and they are excellent for fault clearing capabilities on large overcurrents that you have. And they've got a short fusing or fault clearance time. They are not consistent or reliable on small to medium overcurrents. That's why we shy away from them sometimes. And if you have an incorrect fuse link, you can easily be able to replace that for a blown one even though it's not specified for that. So in that way, it saves you having a long downtime. You just take the fuse link that you have and you can put it, because they are housing where you put in the actual fuse. They are all done in a standard manner. So the size of the housing where the fuse fits is the same. And this, ladies and gentlemen, is the last part of the slide. I now expect you to go into your exercise books and do exercises 1. Then you will get a tutorial tomorrow. Thank you.